All right, good morning. Welcome back. Hope you had a nice break. And now we have 4 intense weeks left, right? Well, actually 5, I guess. Although it's scheduled review the last week. So that's what's going to happen. And a bunch of things. And you all know homework's due, and for next week as well. Program assignment, I'll talk a lot about today. You couldn't really start with it much before now. I know some people I've seen on Piazza, and people have asked about how to start, but you don't even know about the main method you're going to use until today. But from today, it's 2 weeks, and after today's lecture, you should be all set. And we'll discuss that method in particular, which is something called Runge Kutta. This is very important. I mean, sometimes I say that things are not so important. So now you have to trust me when I say that this is important. This is probably Runge Kutta methods. These are methods that are used all the time for solving these problems. And that's what we're going to do now. Also, just administratively, I posted earlier today that tomorrow I have to move my office hours. So, if you want to come tomorrow, 11 to 12:30, I know it might not work for everyone, but I'm still there Thursday as usual. So hopefully that's fine for you guys. Let's go back and review a little bit. This we never really had because you didn't have homework on this due today, right? So we didn't cover it, and it went a little too fast last time. So I'm going to go back to 5. This is 5.3 in the book, higher order Taylor methods. This is a way to make those Euler methods more accurate. Should I kill that one? Maybe. But then it gets too dark for here. Anyway, we're talking about Euler. Euler's method, it's pretty clear. You've done homework on it. It's a very simple method. We teach it in Math 1B. It's the idea that let's go back to Euler, basically look at, depending on how you see it, but you can look at the Taylor expansion for the true solution about a point ti. So pretend that you're standing at ti. And then you want to take a step. We call it a step because you want to go from ti to ti plus 1, and you want to update and figure out what is y at this new time. Okay? You want to solve the equation approximately numerically. And one way to do it is to say that this line up here is, of course, true for the true solution, namely that it's really just a straight line with slope y prime plus a quadratic term. And that sounds bad, but the smaller this h is, the step that we take, the smaller this quadratic term is. So maybe it's decent to just approximate by the first one. So that gives a method saying that take the y you had before, add h, the step size, times the slope at that point, which you can compute, and you get a new y. Okay? I'm emphasizing this. It's stupid, but I'm emphasizing it because it shows how we're going to make it more accurate later. It's clear that every time you take a step like this, you make an error that scales like h squared, which sounds pretty good. And we saw with the proof of the Euler convergence here that it is good enough in the sense that it will give you the true solution if a gets smaller, h gets smaller and smaller, but quite slowly. So in particular, we proved this error bound, which says that so the way you use this, some people asked about what is ti, what is wi. This is true for any I. You have to imagine that you're solving a problem where you're going to go from A to B. A is often 0, it doesn't matter. But you want to go from a starting point to some end point, right? And the little technical issue is that as h goes to 0, the number of steps goes to infinity. So you have to be careful. And in particular, when we did this proof, we noticed that there was both an n, the number of steps, and an h. And they had to be cancelled out so we could eliminate. Very often, this is just written as one big constant times h. Sometimes you want that big constant. You had homework where you had to actually look at it. But I told you it's kind of worthless in a way for most practical problems anyway. The big deal about this is that it scales linearly with h. So a typical question would be, what happens? You have an error. What do you expect the error to do if you divide h by 2? Well, the error only goes down by 2. And is that good enough? Maybe it is. For our little silly test problems, it wasn't clear. I mean, it's very hard for you to say, what is my model problem? I think my model problem is this really horrible e to the t, right? So y prime equals y. And this is, you do much more advanced things in your homework. But what I was saying was that if you do 10 steps on this, between 0 and 1, then you get an h of 0.1. And remember how I implemented this by saying that w starts at 1, for example. I did these before. Let's call it n. And the next w is the previous one plus h times the slope at, well, the next one. I forgot to compute this one. And the previous solution. Sorry. This is it, right? So, you know, these are type of codes you will write. I said don't write inline like I do here. You make mistakes, it makes it easier to put it in files. But for now, I don't want to flip back and forth between windows. This is going to break because I didn't find t. Let me do that. T is 0 to h to 1. Now this works. And it gives you a solution that I think many of you would say it looks pretty OK. Of course, you want to compare with the true solution, so we plot it at the same time, which is that, right? And actually, it's kind of nice when you compute numerically, since we step. It's not a bad idea to put little markers sometimes, so you see your steps. And another question, is this good enough? And if it's not, you just refine and keep on doing it, right? But I'm telling you that for the most trivial test problem in the world, taking 10 steps and getting an error of like, you know, just roughly 10% or so over there is not good. This is not too impressive. So we're going to see if we can improve on this. But having said that, it's obvious why Euler is the most talked about and the first method you learn about. It's so straightforward, it's so simple, and it actually does work. And I did show, I think, last time that if you just rerun what I just did with n20, that's half h, it goes almost exactly in the middle between these two. So the error did go down by a factor of 2. And you might want to think about why not a factor of 4? Every step you take is, as we said, making an error of h squared in the prediction. If you want to predict from ti to ti plus 1, and you're making an error of h squared, why now suddenly is it just linear? And the reason is basically that as h gets smaller, you need to take more steps to get where you want. Okay? And I did draw a little figure of that last time, saying something like this. Just take some thin chalk. I think I did just 2 steps. Suppose you're standing here, and the true solution looks like this. Now you want to go all the way up to the next time step. And you do so by, for example, doing one Euler step like that. And then this was kind of bad. But we said this here was basically scaling with h squared. What do we mean by that? It means that if I only go here to ti plus h half, we expect this error to be a quarter of that, right? So the error if you go from here in a straight line, a step of h is h squared. So if you only go half, you're making a quarter of the error. Okay? Now let's see if we can understand why the actual error then is not h squared, but just h. Because you end up predicting the wrong thing, right? So in the real world, I would ask, for example, for an approximation to this value, right? Or actually, I would take many steps. I would ask for some value here. But let's just say this particular problem. When I divide h by 2, I tell you the answer at the wrong point, right? If you want to give me the answer to that, you have to take another step. And roughly, you're going to make another quarter error when you do so. And going to end up adding up those quarter errors roughly, right? It's a little hard to illustrate now. Now you're on the wrong solution here, but you're going to make another quarter error in the next step. But roughly just you're taking 2 steps in order to get to the same point. So even if you have 1/4 of the error, you get roughly 1/2 when you add them up. I mean, the formal proof of this is, of course, what we did. And there was this n that ate up one of the h's. That's what happened. But it can be understood in this sense. It's kind of fundamental. It means in particular that you needed h squared in 1-step error. Otherwise, there's no way you can be convergent. So can we make a worse method than Euler? I mean, there are bad methods. But let's say we can be lazy just looking at the Taylor. Could we skip this term, for example, and do even lower Taylor approximation? Well, if I say that y of ti plus 1 equals y of ti, and then let's stop. I could do that, right? Is that a good method? Well, each step will be making an error of order h. So again, if you make the mistake of not adding up, you would think that as h goes to 0, the errors go to 0. And they do. But how stupid is that method? That method says that the next one is the same, right? That's a constant solution, right? And the truth is that for 1 step, it is really getting smaller and smaller, but you have many steps. So it's not convergent, of course. Because it's going to tell you that the solution is equal to the initial condition always. Very bad method. So this is kind of the worst method you can come up with, Euler. That still works. OK, so how do we make it better? Just going back to, and by the way, just the terminology here that we're going to keep on talking about later. When we did the proof there, we were very interested in this error here. And it's called, if you divide it by h, it's called the local truncation error. OK? So let's see how it's defined. It's a little tricky in a way, but it's in order to generalize that this is what I would call, many times we call it a one-step error. So suppose you have a method. You can pretend that this is Euler's method for now, but this phi is going to become something else later. But if you pretend that that phi is equal to f, it is, of course, Euler's method, right? And then we find the local truncation error to say, suppose you're standing at yi, and you're taking one step. Then this would be your new numerical wi plus 1, right? But then what is the error between that and the true solution y? So it's exactly what I did here. You're standing at yi. You try to take a step. Divided by h, and we call that the local truncation error. This is just a definition, but we will be using it. And in particular, you can see that the Euler's method has a local truncation error of h, order h. Why? Because if you look at this line here, Euler's method is really taking this term here to be your wi plus 1, and the difference between these two is order h square. And then the definition for local truncation error divided away on h. But you'll see more examples of this soon. Anyway, here comes now the punchline. We're going to make it more accurate by simply including more terms. And let me warn you that this method is not that practically usable. The Runge Kutta methods, the topics of today, are more useful, but this is the way to learn them. Let's go back. We're trying to solve this problem, as you know. And you can look at one big Taylor expansion here. And if you look at the first two lines here, it's a big Taylor expansion saying you're standing at yi. And you remember my shorthand that y of ti, sometimes I just call yi, and there is not a lot of risk for confusion, plus h times the slope, plus h squared half times the second derivative, plus etc., right? And you can go all the way up to n if you want to. And you get to stop at some point, and sometimes there are different ways to do it. You can pretend that it goes on for infinity, but we like to say that it stops with an h to the next term, and it's kind of times something we don't quite know, because there's a psi. But at least it scales with h to the one that you didn't include, right? Let's see what we can do about this. Remember what we did with Euler? Then we stopped already there, right? What did we do with y prime to turn it into Euler's method? Remember the equation we're trying to solve. You don't know y prime. You know f, right? So what we did to turn this into Euler's method was to stop here and say y prime is equal to f. By definition, that's the problem you're trying to solve, right? So that is Euler's method. So isn't it kind of obvious how to make it a little bit better? Keep one more term. What is y2 primes then? Well, we don't know that either, but you go back to the equation and you realize that that has to be f prime, right? OK, and that's the key. That's what we're going to do here. So that would be what we call the Taylor method of order 2. And I think it's pretty clear what the Taylor method of order n is. You just keep on going by including these derivatives. And the problem is in that derivative. It's hard to compute, but we'll see exactly how to do it. So if you look at these next two lines here, I simply replaced all the y primes and higher by f's. So y2 primes became f prime, etc. This is certainly Taylor expansion for this equation, right? And the method is simple. Delete the remainder term, and you get the Taylor method of order n. You can write it out like this if you want to. It looks exactly like Euler. You start at alpha, and you keep on adding in h times something. And that something for Euler is just f, right? But now it's f plus, and there's something else. And it can keep on going if you have the higher orders. The Taylor method of order n. And this is often denoted t parenthesis n. You can look at the local truncation error. It's actually not hard, going back to the entire proof we did before, to realize that this will become, if you go to 2, it will be one step more accurate than Euler. And why is that clear? Remember what we said when we did Euler? We said that each step makes an error of h squared, right? It's pretty clear that each step now, if you keep, let's say, the square term, is going to be the next one, the remainder that you ignore, namely h cubed, right? And what is maybe not immediately clear is that you still lose an order or factor of h. So the final method instead of an h here, would have an h square and somewhat different constants. We're not going to go through that. I'm just telling you what happens is that each extra you keep, you get 1 order extra accuracy here. Okay? And that we have in this theorem here, saying that, well, this theorem actually just says that the local truncation error is order hn, which is trivial, because that's the term we cut away. But that is the higher, that's the higher order Taylor method. This is best shown by an example because it's a little tricky. And I did this example last time. I'll do it again because it went a little fast. I made up, well, let's go even slower and just start with our trivial y prime equals f. You know, I'd like this one, right? So just do e to the t, the one I just did on the computer. Let's do this one with Taylor method instead. And so what do you have to do? By the way, my model problem, I like to set y 0 is equal to 1. OK, so what is the Taylor method of order 2? Well, if you want to, you could go back and read. It's this, right? It's Euler, but one more term in the Taylor expansion. So it would look like this. Taylor method order 2 becomes wi plus 1 equals wi plus h, right? Times. Well, that's just what it says up there. And then it becomes, you get this Tn. And of course, the first term is exactly f, which is, let me just write f for now, Tiwi. And if I stop now, I have Euler's method, right? But I'm going to add in one more, which is going to be, you lost an h there because of the way that they defined the t, they took away one h. It's kind of silly because you put it back here. So sometimes it's easier to keep it. I think it's confusing to have, when I put a 2 factorial there, I'd like to put a 2 there. That's what we do in Taylor. But now they took away an h, so it's confusing, I think. But it doesn't matter. And here comes an f prime of ti, comma w. OK, so this is the Taylor method of order 2. However, it's not practical. You can't use it, right? Because you don't know f prime. So this is the issue, but we'll derive it, so don't worry. The f we know. We could just replace whatever it is, right? But f prime you don't know. Can't you just differentiate this? That's what we're going to do. I'm just warning you a little bit, and you have to review your Math 53 here, that there are several dependencies on t. It's implicit here because we don't want too many parentheses, but the function y depends on t. When we say prime, when we say f prime, we want to see, it's a little bit of abusive notation, but it's clear from this equation that the prime notation means the total derivative with respect to time. So if you go back to your Math 53, you would figure out that f prime of t comma y means that you get a difference. Let me emphasize that y depends on t. Although usually we will not do it because it's understood. OK? How do you do that? Suppose, I mean, to begin with, f does depend on t directly. So if there was no y, this would be a trivial, the good old derivative, right? Let's just to not turn it into a multidimensional problem. Suppose there is no first t, f prime of y of t. OK, so you have a function f that depends on the function y that depends on time. This is the chain rule, right? You got to differentiate, and you got to multiply by the inner derivative, which is y prime. Now we have both. Then we just do the Math 53 that we do each of them in partial derivatives. So I hope you all see that this is really df dt times the inner derivative, if you want to, dt dt, but that's 1. So I'm not going to do that. Plus df dy times the inner derivative, which is dy dt. And that's the total derivative. Sorry. All right. Am I happier? Yes, because I can compute partial f partial t. In fact, for my problem, it's 0. I can compute partial f partial y. For my problem, it's 1, right? How about dy dt, the derivative of the true solution with respect to time? Do I know that? It's f. So that's the key trick here to keep on, to be able to do this. That because we're solving this equation, y prime equals f. There are a lot of cases when the trick is to replace f by y prime or the other way around. times df dy times f. Okay, and you see I was a little sloppy with the notation here. I guess we could put back this if you want to, and just ignore them on the partial derivative. But this is the technique that you do. So in particular for our case, here, let's keep on going here. We can now write the method as wi plus h times f. I'm going to multiply in the h. I don't even approve of that form. Plus h squared half. And then we simply replace by that, right? H squared half times, well, we got to replace it by f prime, which I said is df dt, that's 0. But it's going to be plus df dy, which is 1. So let's write them out. It's going to be 0 plus 1 times f. That's it. Or cleaning up, this was a little too easy. It's really just wi plus h f plus h squared half, again f. That's just because of this equation. Okay? So now I started, this was general. Now I started plugging in my f here. Sorry about the confusion. So here's the general case. Here's a continuation of my trivial f. There. Let's just plug it in because it's so easy to do. Why don't we rerun the same case? You remember the error there. We rerun the same case. The way to put that in here is, I mean, there are various ways. I think I did it in a different way last time, but for now, since we have it, why don't we just add this? In fact, we can reuse the f. It's kind of, just because this is so easy, I can kind of do this, right? Plus h squared half. And now they are right on top of each other, okay? That's enormously much more accurate. Shouldn't be too impressed because it's a very simple equation. But at least it shows that, wow, this was a really nice little addition we did here. I think it's too easy to see. Let me just do a few other ones. We can take fewer steps. So n2 now. And this is why I said you should create scripts, right? So you don't have to do this all the time. Here you have just 2 steps. And it's actually kind of accurate with 2 steps. But what do you expect happens with that gap up there if I now divide h by 2? So now I'm going to do n4, rerun everything. And let's do a hold on so we see both. Make it red. What do you expect happens to that error up at the top when I divide h by 2 for this method? Remember, for Euler, it was approximately scaling with h. So when I divide h by 2, the error, it went straight in the middle, and it divided error by 2. Now it's supposed to do it approximately by h4, by 1/4. So by h squared, which would be 1/4 when I divide by 2. It doesn't look like, it looks like a third. That's because we're not quite in the convergent regime. If I do one more, wrong h. Anyway, if I do one more, what color is this now? We're supposed to, yeah. Does that look more like a quarter? Yeah, kind of. It's supposed to, eventually it will be a quarter. Right? So, you know, it just means that it's a much more accurate method eventually at some point, but even for practical values. Let's do the case I did last time, just because this was a little too simple. So let's just try this formula once more. And on this equation I did last time, I think then I did y prime equals f of t comma y equals, and I made something up, which was y times 1 minus 16t. I start at 1, as I always do. Exact solution we need is going to be y equals e to the, well, yeah, e to the t1 minus 8t. Separation of variables. How do we do a Taylor method for this? Well, you got to compute f prime of t comma y of t. And as we said, it's going to be equal to that. You do a partial with respect to t, you do a partial with respect to y, and you do f. And for this equation, that's a little less trivial, right? Because now there is a t derivative, but it's doable, right? It's minus 16 times y. So, and then you have a y derivative, which is 1 minus 16t. And then you have f itself, which is y times 1 minus 16t, right? You see, it's not trivial, but it's doable. It's just differentiation. And you could clean this up if you want to, but yeah. Let's take out the y. 1 minus 16t seems to come square and minus 16, right? You got this expression, but that's what you need. Let's try to solve it. We just replace. Then probably, I mean, this was a little simple hack that worked just for that equation. In general, how would you do this? If we now have a new equation that says y times 1 minus 16t, I would recommend defining f prime, which is that expression as a function. So then you could just write it in like that. What is it? 1 minus 16 t minus 16. And now the Taylor method is just, so this was a special case, but in general it's really just h times f of ti wi plus h square half times df ti wi. Keep one more Taylor term. That is what the method is. Most of the work, the method is trivial to define. Most of the work is just finding that expression. And if I didn't mess it up, we have now solved, and I need a true solution, right? Y exact. What was that? X of t times 1 minus 8t. There we go. Y exact. All right, so now we didn't compare with Euler. Does look pretty good, I think, for being 8 steps. Of course, to really impress, but you probably have to trust me that Euler. It's a little confusing when things decay to 0, because it looks to be good, and it will no matter how inaccurate it is. I can have 50% error, and as it decays to 0, it will look great. So you have to ask yourself, what is it that you want? But suppose you are interested in the rate, some sort of ratio here, then this looks pretty good. Let me just do my trick of doubling n from before. I had a new t, and we recompute and see if this improves it. Oops, I messed something up. Yeah, I need a new y exact. Anyway, so by the way, did you see one mistake, one bad thing I did now? I plot y exact using the same steps. So let's erase the old one. You see what I'm doing here? I'm plotting the y exact as straight step. That's not true. Y exact is a smoother function than that. So it's not supposed to be straight lines. I mean, in the computer it will always be, but really if you want to be more careful here, you might want to superfine TT. You know, we always call it TT when we plot functions. That's probably better. The numerical solution is perfectly fine to plot with straight lines. It doesn't mean anything, but it indicates that you don't really know what's going on in between. You just have the circles, and you connect them by straight lines. But the true solution you don't want to do. Anyway, you can see that it's if we looked at the other one, we would probably see about a factor of 4 here as well. So that's a pretty good method. That's the Taylor method of order n. Of course, we can just keep on going with one more term, and it starts getting insanely accurate. And that's good. That's kind of, you're going to do some exercise for the homework for next week, but let's just leave this method and figure out what's bad about it. There are various things that are bad about it. It's certainly accurate. It's getting more and more accurate. But the problem is this. And it's not because I mind doing this, because I could have a computer doing what I just did. Symbolic algebra, right? What do you think the huge issue is with this? Well, it just, oh, by the way, I could indicate how to go higher derivatives here as well. You just keep on repeating this if you want f double prime, if you want the Taylor method of order 3. But it does get more messy even doing it by hand. Actually, the main reason this is really not working in practice is that someone usually gives you an f not in terms of an expression like this. Typically, in the real world, you get an f as a black box. It could be that you want to solve y prime equals some sort of data that is fed to me through some machine somewhere. Okay? You just don't know what df, dt, and df, dy are. That's the practical thing. It works for our homework problems like this, and we can make it quite simple, and it's kind of interesting. And it's the right way to learn the next method that we're going to talk about. I'm just telling you that in practice, of course, someone has to give you f. Otherwise, you can't solve. It's hard to, no matter how good you are at solving things, someone has to tell you what the f is. But they might not like to tell you what the derivatives are. That's the problem. So the goal now is to see if we can do this good thing of getting this accuracy without doing any derivatives of f. And that will lead to the Runge-Kutta methods. Or one way to do it is the Runge-Kutta methods. So basically, really, Taylor is great. We just don't want to do that. Let me show you how to do this in Runge-Kutta trick. Here's a slide, which again is just a review of Math 53, and you don't need to worry about it too much. Let's just review what you know. I'm just going to use Taylor in 2 dimensions, okay? And I think it's really easy to remember in a way. It really says that, remember Taylor in 1 dimension said that you can write the function as, you can do Taylor about a point, for example, this t0 here, and it says that it's going to be the function at that point plus a deviation times the derivative times the slope, right? And ignore everything with y. The next term is h square half times the second derivative, etc., right? So if you look at only the t parts here, you really see the regular Taylor in 1 dimension. And it ends at some point. This is, of course, a mess. Now, if you now have another variable, you, of course, get exactly the same story there. So you get a df dy times the jump in the y direction, etc. And you also get the mixed derivatives, because now a second derivative involves mixed derivatives. So I think in math, typically we go up to this level, and we kind of start thinking that now it's getting complicated. I don't know if you've even seen this expression for the remainder term. There are a lot of terms here. If you go up high and down, you have to write all these derivatives out. So that's what's going to happen. But luckily, I kind of just need the first line here, which is really just saying that something is a plane. It's like saying that it's like the straight line approximation in 1D. It's a plane, right? So here's the setting. You have a function f, and it can be written as a Taylor polynomial plus a remainder. And that Taylor polynomial is really just the value of f at that point plus the slopes in each of the directions times the jumps in each direction. And you know that this leads directly to approximating a surface by a plane touching a point, right? So that plane has the same tangents and the same value, but apart from that, it's of course wrong everywhere, likely. Just like a straight line is wrong everywhere if you don't. I'm just going to use that part, but of course the next term we can also observe involves quadratics in everything, either in t or in y or in the combination. Okay? So don't worry too much about it. And there is an even more. Oh, yeah, this was the last term. The remainder term comes here. I don't know if you've even seen this. It's a mess. But you can identify a few things at least, namely, again, that the order of these terms are going to scale. If both of these scale like h, you can determine the order. But we're not going to go that far. So don't worry about it. Let me tell you how to try to produce a method as accurate as what we did here without using derivatives. It's a simple little assumption that 2 people, Runge and Kutta, are getting credit for. And here's what they said. So, so basically the starting point here is that we kind of like the Taylor method. We like, remember Taylor method, Taylor, order 2, I'm going to write it again. It says that wi plus 1 equals wi plus h times this t2. Okay? And it's going to be a function of ti. Okay, and this t2, we said, I'm going to define it in terms of t and y, to say that this is really just equal to f. And now I'm going to start dropping parentheses because it's getting messy. F plus, and we said, if you go to 2, you get this f prime. Okay, so this is what I did. And then we took all that, what we did over there, and we replaced this f prime by, we're getting f. We're getting h half times f, and I'm going to use the subindex of t to indicate partial differentiation. You're fine with that, right? I just want to keep this shorter. H half f y f. Okay? I really just repeated what we did before, but in a briefer language. In particular, I replaced f prime by df dt, which I call ft sub t plus df dy times f, so that's really fy times f. Okay? So here's the method that we like. Can we do this method without computing these guys? That's the question. All right? Try to approximate. It won't be exactly this. Without derivatives. And to not make this look like I just made something up, what could we possibly do? I'm telling you that you have f, and I don't want you to evaluate derivatives. What else can you do? I mean, it's like you have evaluated f already. It doesn't seem likely you'll be able to rewrite this expression knowing only f, right? Because there's an f, but here's a df dy and a df dt. It doesn't seem likely you will get away with just f at the point ti, wi. So what power do we have with the f? Well, the Runge Kutta trick is to start moving around a little bit. Remember, when I say f here, I'm implicitly talking about f at the point where you evaluated t here, which will be the ti, wi. If you move a little bit away with f, you can actually start getting other terms into, and you will actually get exactly these terms showing up. But we will try to approximate it by a little form, by a form like, let's see, where did I put it? Here. We might want to multiply it by something, but it turns out it will be 1. But the key is to move a little bit away. I don't know how much. Okay? What I'm saying is that instead of evaluating f, every time I skip the parentheses here, I meant t comma y. Okay? I'm saying, what if I just move a little bit to the side? This I can do because you're giving me a function f. I didn't say that you can't evaluate f anywhere. You can do whatever you want with f. I just don't want the derivatives. If you think about it, if you expand this in Taylor, and this is why we needed the multivariate Taylor, you get a bunch of terms. And maybe we can identify and try to make it match that. Okay? And let me first show you how I think people actually thought of this method without doing the algebra, or the calculus, I guess. Here's a method that it's going to lead up to. You're standing here, you want to get to here. You're taking the Euler slope, and you realize that Euler would bring you there, and you don't like it. So what the method does, and I think you can often reason a little bit why this might be a good idea, but the method we'll end up producing here is going to take a half step. Okay? That doesn't help you much. At that point, we're going to compute a new slope, which will likely be different than the original one. And we're going to go back to the original point with that slope and go there. Okay? You'll see when I write the expression. I'm just telling you that there are geometric interpretations of all these things we're going to do. And just based on my little figure here, assuming this slope would be leaning a little bit more upwards, it looks like it should at least be a little bit better than the Euler step. But it turns out it will be very similar to the Taylor step. We'll come back to it when we see, and I'll write some notation for all these slopes in a bit. Just wanted to give you a heads up on what's going to happen. So if I Taylor expand this, and I match terms so it looks like this, approximately, then I can use this instead. And this is fine. That's the plan. So let's just Taylor it. Multivariate Taylor. Variate. Well, it really just says that that thing here is, let me write it again. So I want to take f over t plus an offset. I don't know these alphas. I don't know anything. We're going to identify it later to see if it works. But I can tailor this and say that it's a1 times f of t comma y. Now I keep the parentheses because it's important, because I'm going to make offsets here. And remember that Taylor was really very easy. The first term is very easy. The 0th term is, of course, trivial. The function value itself. The linear terms are really just saying a1 just keeps on coming. The step you're making in the t direction, alpha, times the partial derivative with respect to that dimension. Right? So there you get an ft, t comma y. And then the next one is the A1 comes along. It's going to be the step you're making in the y direction times the partial derivative with respect to y. That's it. But there's a remainder term, but let's skip it for now. Well, let's not worry about it. But there is a remainder term, and the idea is that that's going to be higher order terms. Now, remember the goal was I like this method, but I want to compute it by stepping a little bit alpha 1 and beta 1 away. Can I do that? Well, now we're going to play the matching game, if there is such a game. We're going to try to identify what these could be. And you can see that I better make A1 equals to 1, and you could argue that in many ways. It was kind of stupid to have it there in the first place, but just because we could, let's put it there. What do I have to set alpha to? There's a df dt, right? And over there, alpha. So it looks like I should take exactly h half step in the t direction. This alpha 1 should be really h half, which is good. And the beta, well, I have a term here saying 1 times beta 1 times df dy. And I want it to look like h half fy times f. So the fy is there. It sounds like beta 1 should be h half times f, which is excellent because I'm allowed to evaluate f. So beta 1 should be h half times f. Again, evaluated at t, y. So all this is trying to do is to say that you can do this instead. This leads to the so-called midpoint method that I illustrated here. Let's put it here. This means that you can write this guy as, I'm going to say approximately equal to, and I'll tell you why, as this instead, with these numbers. T plus h half, comma, y plus beta 1, which was h half f. Maybe I should put the arguments on f, just for the sake of it. OK, that's what I identified, right? So this is the method. Is this more useful? You see there are no derivatives. There is a slight issue. I have to evaluate f twice, but that's OK. I have to pay some price, right? But I really did something that is, to some order of accuracy, as the same thing as before without using derivatives. This is the midpoint method, and it's quite popular. Let's go back to what it means. You can see that it's not identical to this. Why? Because of this remainder here, which will likely have some extra stuff, right? But we'll argue, and it's in the slides, I'm just not going to repeat that. We'll argue that these remainders are all of the order of h squared, which means that it won't really mess up the method. So it's a different method. It won't give you the same result. But you must appreciate the simplicity when maybe we should just code it so you see that it's so much better than what we did before. That now the method looks like this. Let's keep the old one. All right, I don't need df, right? I need this. I'm going to take h times parenthesis. And then we just replace it by what we have there. Well, no, there's no parentheses there. Here you better put h half. Here you better put h half times f. And that's evaluated at the old one. Kind of nice, right? Unless I messed it up. Hold on. Let's make this green. Well, it looks more accurate. I don't know if that's a coincidence. They are not the same method, but they have the same order of accuracy. It's possible that this is a factor of 2 smaller error. You could do that study. But the point is that it's kind of amazing that I produced the red curve here that I liked by simply replacing this term here by things involving f. That's a Runge-Kutta method. Right? You might not be impressed, but if you were sitting there with a black box f, and someone asked you to differentiate it, you would probably be quite happy if I told you, look, you don't have to differentiate it. Just evaluate it, do these little arithmetics here, and evaluate it again. And it will give the same method to the order that you're interested in. Before going on, let me just write it in a way that we like to write these terms. It's just a coding type of issue. Practically, you often do it like this. Implementation. We're going to have, turns out we're going to have a lot more complicated nested things like this. So I'm going to try to unnest it and realize that this is ft2. There's an f there, and there's an f there. And in math language, it's nice to just write a one-liner like this. But in a computer code, we like to split it up. So really, what you do in a computer code is that you do for I equals 1 to n. Often when I write computer code like this, I deliberately don't make it exactly MATLAB, and I call it pseudocode, just so it's not supposed to be exact. It's kind of, that means that you can cheat a little bit and write words and stuff that you wouldn't write in a computer code. But what I want to emphasize here is that you compute the case. So you define a slope, which is this f here, of ti, comma wi, okay? That's the number here. Every time you evaluate f, you call it a k. So now you call it k2, and you say, and I think the book likes to put an h outside there. That's usually not done. But we're going to do it because the book does it. Then you have k2 that is done what? Now you write this in terms of the k1 here. So it's going to be, of course, just ti plus h half. And this is going to be wi plus k1 half. So it's a very short and nice formulation where you evaluate a bunch of k's with some arguments involving k's like this. You see, I unnested it. So now there is no longer any f inside the f here, but they're written on separate lines. And what in the very end is then wi plus 1? It's wi, I guess we got to go back to the method, which says that you got to do wi plus h times this, right? Which I already included in this here. So it's really just k2, and you're done. And I know, why did I do this? You'll see for the next method that this makes sense. For now, I just want you to agree that the method I have over there with this f here is, of course, identical to doing it this way. OK? I unnested it. And this is typically, you identify a Runge-Kutta immediately by these k's, these slopes. It kind of builds a bunch of slopes only using f. And then it adds them up at the end. And there are different ways you could add them up. And I'll show you some other method. Of course, for my one-liner here, this was not so. This was kind of more convenient because I like to write things on one line. But that's not the way you should write computer code. And I'll show you how to write a more, we could write the special of this, but I'll show you a more advanced function that you'll be using anyway. So let me go back to the slides and just catch up on it. The derivation with more of the error terms are here. In particular, there is the matching of the coefficients. But there's also an argument, and it's, well, not too much here, but more detail in the book, showing that this remainder term that I skipped is really h squared. So that motivates this method that is called the midpoint method. And it has a local truncation error of the order that we want. It's really very similar to the Taylor method of order 2. Not the same method, though. Here's probably the most used method in the world, after Euler. But I don't think people use Euler. People talk about Euler, but it's so bad, so you don't use it. This is RK4, Runge-Kutta method of order 4. It's, they invented it a long time ago, and it's used a lot. And you can see why I want to split it up, because now they follow exactly the same pattern as over there. It's just that they compute many more k's. And it's beyond the scope of this course to analyze this method, but you're going to use it. Okay? So this is, if you don't mind, just what we just did, and we completely understood this midpoint method. We saw that it was accurate, and we could write it like this. Trust me that you could turn the crank here on a lot of algebra and a lot of Taylor expansions and actually get a method. So what is this method using? It has exactly the same characteristic. It has all these h times f. So the first line is actually identical. h times f at ti, wi. But then it starts adding in a little bit of h half, a little bit of k1 half here, and computing new f's and calling them k2, k3, and k4. And it's not at all clear why these are h halves and why these are k1 halves and k2 halves. You have to analyze it to see why that's there. But in terms of using it, it's obviously quite straightforward. At the end, you have 4 k's. And in this case here, we just added k2. That was this method. But in general, you want to do a little bit of all these slopes. And in this method, you do 1/6 of 2 and 1/3, 1/3, and 1/6. This is an insanely accurate method. It's 4th order accurate. It's quite easy to implement. It has no derivatives. There's a reason that it's quite popular. You can do a graphical visualization of it, but it's a mess. I don't think anyone sees what's going on. Let's go back to try to motivate now that I have this language here. Let me motivate this figure again. You're standing here, OK? At ti, and of course, the value here is wi, right? You're supposed to take a step, and you do so by computing a slope that we call k1. Okay? And maybe just technically speaking, when you multiply by 8, it becomes an offset, not a slope. But I don't care. It's a slope. F is a prime. It's a y prime, right? So we call them slopes. So essentially, you're computing this Euler slope, and you can call it slope k1. Right? And you know that if you take that times h, or actually k1, if you just do, by the way, what is Euler in this language? You all see that if you skip k2 here and do k1 there, you have Euler's method, right? So Euler method is a Runge-Kutta method of order 1. You just add in there, right? So if we do a full step of this k1, we'll end up there, and we don't like it. Instead, what do? We step half the way, just h half, and we add in, this is like half an Euler step, wi plus k1 half. So you go out here, and you compute a new slope, and you call it k2. And maybe it looks like that. k2, slope k2. All right, what do you do with that slope? That's the last line. You go back to wi, and you take a full step of slope k2. And there are geometric reasons why you could argue that this has to be better than just plain Euler, and even arguing that it has to be 1 order more accurate. But I just wanted to show that these slopes, the Runge-Kutta method is bouncing around with these things and doing its best to try to. There's very little you can do. You can just evaluate f at various points. And you want to try to cancel out all these terms that end up here. It's kind of a game to play. And imagine a number of terms to make this method here accurate to that order. People usually do this with computers, but this one you could do by hand quite easily. Anyway, so that's the Runge-Kutta method. Let's look at the implementation, because this will be important for you. This you don't want to write as one-liners as I've been doing. And I have provided a code for you that you can use, and you should read it, and you should see what's going on. It's called RK4, and it's on the web page. It's remarkably short. It looks a little bit messy here, but it's just repeating things after each other, so don't worry about that. Let's see what's going on. Maybe I want to put up the method at the same time. Well, there it is. But let's put the method here and the code here and see if we can identify things. Bigger method. And out there. All right. Now let's see if we can identify how to implement this. So first of all, you have to look at this function. This is a function that solves a differential equation for you numerically using RK4. You, of course, have to tell it a bunch of stuff, right? F is a great thing to tell it. And if this was a Taylor method, you would probably have to tell it the derivatives of f, because you're the only one knowing it using all those mess from before. But this is a Runge-Kutta method. All you're telling it in terms of the function is just f. Of course, it wants to know where to start and where to end, right? A is very often 0 in our cases. Alpha is our notation for the initial value. N is the number of steps. OK, sounds reasonable. What are you getting out? Well, it's not clear, but you're getting all the W's, of course. That's what you want. It's also nice in giving you all the T's, even if they're trivial, it's convenient to have. Let's look at the code. It computes an H. Remember, in my cases, h is always 1 over n. That's because I goes from 0 to 1. In general, it's b minus a over n. That was easy. Since you promised to produce this time vector, you better do it. And it's going to be a in steps by h all the way to b. This is the MATLAB syntax for creating an equally stepped vector from a to b in steps of h. W, it looks a little tricky now, and that's the topic of the next part, that this is actually a more general and handled system. But for now, it's just creating a vector of length alpha to put all the results in. Oh, sorry, of length m plus 1 to put all the results in. And at position 1, it's putting your initial condition alpha. Okay? So it's going to create a long vector with all these w's, just like I did in my demo, and start at what you gave it, and then keep on stepping. And here comes the main loop. You take n steps. For each step, you compute these 4 k's. And they're really just h times f's. But the thing you send in is different. So the first time is really just like Euler, ti, wi, but then it ends up being these various ones, right? So the next step is really exactly our midpoint method. But then it goes crazy and it's doing other things. And at the end, it adds these up in a non-trivial way. But it's all according to this method on the right. So going from this mathematical description to this code, it's fairly straightforward. It's not a unique way to do it. I defined a lot of parameters, but it can be done. When you have it in this form, of course, now we can easily use it. Let's solve the same problem as before. Using this method, we have an f, right? Yeah. Remember this? This is my test problem from before. The way you run it now is just to do RK4 of f from 0 to 1, starting at 1 in. You're not going to need many steps. That's the amazing thing here. But we can do 5 steps. All right? Out comes the t. That's not too interesting. And out comes the solution that it computed for you. Of course, what we want to plot here is, do I still have these other ones? What colors are black? All right. Now, you see the black curve? Maybe you're thinking, oh, it doesn't look accurate at all. That's because I'm drawing it the wrong way. Okay? It computed 5 numbers for me, 6. Well, it started and then 5 steps, right? What you have to look at, I'm drawing straight lines. I'm not supposed to do that. What it predicts is this number here. Okay? And it should be compared with the true solution on a fine scale. So let me replot just to show how accurate it can be. If we do a finer scale like this, remember I said that this is the way you're supposed to plot. Okay, so now I plotted it correctly, where you have the Runge Kutta and you have the true solution. And it's actually, maybe I pushed it a little bit by doing 5, but you see how extremely accurate it is. With one huge step here, the curve is going through a lot of curvatures. This is the power of 4th order accuracy. Down here, we're not that happy. It's just not capturing this curve down here that well. Is my y exact, really? Yeah, I guess. And my f is. All right. So then you just compute a new one with 10 steps. And you plot that instead. And now it looks much better. So here's a question. What do you think? I told you before it was a 4th order accurate method. And in the slide it says it has a truncation error of order h to the 4. So what approximately, if I looked at the errors here in detail, how much did it go down now? This is like 10 to the minus 4 now. How much did it go down compared to the previous case with 5 steps? I have 10 steps now. So I divide h by 2. Euler gave me twice half the error. Taylor method of order 2 gave me a quarter of the error, right? Well, this is 2 steps more. So it's really a quarter to the power of 4. It's 1/16th of the error. So if you're not happy, you divide h by 2, and then you nail it. That's how accurate this method is, basically. So you can use this method. Now, if you didn't understand some of these colons, there are a lot of colons and stuff here. That's because this is vectorized to handle the next case. So let me talk a little bit about that. Here's the code again, by the way. Let me jump to 5.9, because things come out of order because of the problem set. Here we go. So first, I'd like to mention one thing. What if you have a system of equations? Everything we've been doing have been, all these things are just scalar. So f is a scalar, right? Y is a scalar valued function. But you should know from Math 54 at least that you want to solve systems of differential equations. How do you handle that? How do you think these methods are going to handle that? You can go through and realize after a while that it's really not a big deal. It's really just integrating all of them separately using this method. In the book, they make a whole chapter out of it. Usually, that's not done. Sometimes it's derived from the beginning by simply saying that everything could be a vector. Okay? So let's look a little bit at, or just to motivate you, all I can do easily is Euler's method. But let me just tell you what would happen with Euler method. So the topic here is how do we make a system of ODEs? Okay? And just as an example for something, the simplest thing I can think of, instead of y prime equals, you now have a y1 prime equals, let's say, y1 plus y2. And the y2 prime equals maybe minus 2y1 plus, let's go crazy and do e to the minus y2. Okay? I just made something up. Initial conditions, of course, you need y1 at a to be something, and y2 at a to be something else. This is a system of two differential equations. If you're lucky, they are not coupled. Suppose I take away y2 there. Do you all see that that makes you happy? Because then it's back to the scalar case. You solve that first and then this. But in general, that's not interesting. In general, they all talk to each other. Okay? And that makes it a true coupled system of two differential equations. Now, of course, in Math 54, you talk about solving these, although not this. But you learn all about solving it when it's linear. And you diagonalize, and it's e to the whatever, right? So you know that stuff. Let me just talk about how to do this numerically. So what do you think Euler wants to do here? And before going on, you will write it in vector form. In vector form. So I argue that you can write these things as a vector y with a time derivative equals a right-hand side f, which is also a vector, and it depends on time, and this vector y. All right? What did I do? I really just identified that you put all your y's in a vector and call it vector y. So there you have y1, y2. All right? F is now a function of time like before, but of this vector. But f itself is a vector. Why? Because you need one equation for each component. So in this case, f vector, is whatever I had there. y1 plus y2 minus 2y1. This is a do-nothing step. I didn't really do anything. I just claimed that when you have a system of a differential equation, you can really write it in this form. It's identical. So vector language is very convenient. And by the way, there's an initial condition, of course, but that's obvious. Now let's talk numerical method. What do you think Euler wants to do with this? How would you generalize Euler to systems? So the way to draw it is, of course, that you're standing here. Or here's the true solution of y1. And here's the true solution of y2. They talk to each other. You're standing somewhere at ti. And you want to take a step up to ti plus 1. Would you be able to do this with Euler? So the short answer is that it's completely trivial. You could think about it, but it's really exactly what I think you would all just do it right if you tried. You do one Euler for each. Okay? So this guy, of course, has a slope, right? And it wants to go there. That slope is exactly the first component in this vector, or in that equation, right? So you evaluate that, and you take a step. This guy has another slope, and it uses it to step over there. That's exactly the second part here. I think I've convinced you that Euler method can be written like this. Well, you start somewhere, but it's a vector now with two numbers. And of course, you have to give me two starting conditions, alpha, for where you start. That's not so interesting. The method itself said that the next one is the previous one. What did I do? So you might want to split it up, but if you think about what I did, I really just did Euler steps for each of the components. Do you all agree that this can be written as h times this vector f of ti, wi? It's identical. I just put vector signs on it. You might want to think a little bit about why it works, but this vector will, of course, there are two rows here, right? There are two numbers in w, not to be confused with the I. There are a lot of steps, but for each of these w, it's two numbers, y1 and y2. Of course, f also gives you two numbers, what are slopes. And you do h times that and add up, and you're getting that. So that's how easy it is to generalize this to systems, and sometimes it's not even described. It's just derived as systems in the first place. If you want a more fancy method, like this fourth order Runge Kutta, in LaTeX, which is the language we write these math notation in, we put bold symbols for vectors instead of arrows above. But all these bold symbols are there to indicate that now it's a vector-valued function. All right? So that's kind of cool. It's identical to before. You might not remember the numbers. It's identical. I just made things vectors all over the place. And here's another good news. My function is written to handle this. So if you want to, and that you have to think is a little bit, that's slightly more advanced MATLAB that you can look into. But the reason for all these W parentheses I, comma, colon, etc., is to make sure it works. But you don't have to worry too much about it. You can use it as it is. To solve an example, what you have to do is like this. Let me show you a simple example. You define an f like before. MATLAB doesn't even have a vector notation, right? So I'm going to call it y, and I'm just going to say it is a vector. I wanted it to be this equation here. So your f is really y1 plus y2. I don't know if this equation makes sense. And then there's another one that is this. This term would probably kill everything. You see what I did there? I wrote a function f that takes a t that I don't care about, and a vector y. I assume there are going to be two numbers there, so I'm going to talk about y1 and y2, and I'm going to produce a vector f. When this is done, you could do Euler or whatever, but let's use this RK4 on it. And I haven't tested this, so I'm sure it's going to crash. Let's start with alpha. Let's go slowly. Initial condition alpha. I don't know, but it has to be a vector, right? And now you can just run it like this. And what else? Number of steps. Oops, from 0 to 1. Well, that seems to work fine. Why are there two lines? It's a system. It's y1 and y2. I don't know which one is which. Maybe we should go further. Let's go to 5 in 100 steps. Oops, yep, this is an issue. This is chapter 510 of the book. It's a bad equation, so it's because it's blowing up. Let's go to 4, so we don't see that. All right. We just avoid. When things blow up, bad things happen. But that's OK. I don't know how to better describe it. When you play around with this, in fact, your programming assignment is all about this. You'll get used to it. And it's so obvious in a way that it's hard to describe. If you just think of Euler component by component, you realize that it's really just put vector sign on everything, and you can handle systems written in this form as easily as scalars. And that's what comes out of it. Now, finally, a few words about one particular set of systems, namely higher order. And this is a trick that you might have seen before. And let me show you the trick. High order ODEs. Very confusing because high order is a term we use for accuracy of our method. But if you go back to differential equations, you realize that they didn't talk about numerical methods. They still had something called order. which was the maximum number of derivatives in the functions, right? So all our equations have been first-order ODEs, possibly systems, right? Guess what? A lot of things in reality are higher order, in particular, for example, second order. This here would explain a lot of phenomena in nature, such as a damped vibrating spring, right? Can we solve this using our methods? Well, we will, but not as it's written. We really assumed that everything we do has the form y prime equals f, right? So it certainly doesn't look like we know how to do this. And maybe the first goal here, maybe the first thing people would do is to say, wow, we need a new set of methods. And you start doing Taylor and everything, right? You can come up with methods for this. But here we're going to do something much simpler. We're going to rewrite it in this form and use the methods that we have already developed. And it's actually very easy. You introduce new variables. In fact, I just need one new variable, but for consistency, I'm going to rename it. So I'm going to say I have a u1, which is the y. So I just renamed it, because I'm going to have a u2 that is the y prime. All right? So I turned it into a system of equations, and assuming this y was a scalar. It could have been a vector by itself, but let's say it's like this. How many equations do I need? Here's one equation, right? So we're going to try to incorporate that. But that won't be enough. I'm going to need one more equation because I have two unknowns. Or in particular, I need a vector f in these two components. So let's look at these components. What is y1, u1 prime now? u1 prime. It's u2. It's an equation. And it's important. It has to be there. It's trivial. But it's the first, it's the thing that was here before, right? It's the first slope of my f vector. What is u2 prime? Well, that's the equation. Sooner or later, the actual equation has to come up, right? But now the trick is to realize that this here is really just the first derivative of one of our variables, in fact, u2, right? So if you move that over, this stuff over to the right, and I guess one little confusing thing is what you're going to do with this. But if you remember, in your right-hand side here, you're not allowed to use any primes or derivatives, right? So to get this to work, the y prime here has to be a minus u2. And the two y's are, of course, just two y's, but we call it u1. That's it. Did you see that little rewriting? So in words, you introduce a new variable, that is the time derivative. You isolate the second derivative by moving things over to the right, and then you just replace, so you have a first-order system of exactly the form that we want. It's very convenient. I can solve it in almost immediately, just like before, by just doing this. Y of 2 minus y of 2 minus 2 of y of 1, right? What happened with the initial conditions? How many initial conditions do you need for this? 2, right? Remember that from Math 1b, that if you need as many initial conditions as you have orders here. Now, it could also be a boundary value problem, where you're given a and b, but that's not what we're doing in this chapter. In chapter 5, we're doing initial value. So you have to assume that you're given y at some point a and y prime at the same point. Let's call them alpha 1 and alpha 2. Okay? Now, we rewrote it. We better rewrite the initial conditions. And of course, our initial conditions are going to be that u1 is equal to alpha 1 and u2 is equal to alpha 2. Kind of trivial, but it's worth noting that we're getting a second-order differential equation of a scalar u. Why? We're told what the value and the derivative are at point A, at time A. We rewrite as a system of two equations, u1 and u2, which is now a first-order system of exactly the form we like. But of course, we need an initial condition that it's a vector. It also has two components, right? Just like I did here. So let's say we start at 1, 1 and run our Runge Kutta again. Then we get some solution out. And And if you plot it, why are there two? Because there are two W's. You get all these numbers, there are W's. This is in the slides. There are a few pages about how this works out. This technique can be generalized, and you can see, we'll come to that later. It's not that critical for now. What I want to show you is a little bit on the problem set. Sorry, the programming assignment. So it's a great idea to start doing the homework for next Tuesday as soon as you can, because you will reroute some model problems in this way. You will do exactly this. And then you're all set when you're doing it in the programming assignment. So in principle, you know now what you need for the programming assignment, but I can recommend doing some of the homework problems. Here in this assignment, you're doing a double pendulum. It's a really cool mechanical system, and you can YouTube some cool videos where they have robots balancing it and everything. You know how hard it is to balance a pendulum? Imagine one pendulum on a hinge like that. People that are good can actually balance like that, right? Double pendulum is crazy. You can never balance a double pendulum, but robots can if they're a really good control system. It's a cool system. It's used for nonlinear dynamic systems to understand sensitivity and chaos and stuff like that. I have an example here just to show you, because I gave you a function that animates it. So here's just a made-up example that shows what this pendulum could do. This is not physics. I just made it up. In fact, the motion was something, yeah. You know, when you run this, if you get it, it's actually, you have to look at it a while to see, yeah, it's probably wrong, right? Unless it's down. It's going to go crazy in your examples. So that's what you're going to do. You're going to solve the real physics system. And I gave you the equations. They are messy. Here they are. You're solving for just two things, angles, theta 1 and theta 2. If you know theta 1 and theta 2, you know the entire configuration, right? But they're functions of time. The equations are just like my example, written with a second derivative. And the very first problem here, you're supposed to rewrite this into first-order equations, just like I did. Okay? It's actually as easy as this. But you know, there are ways to mess it up, as you'll see. Then in number 2, you just send this to RK4, and if you do it right, you'll get beautiful motions. And I suggest 4 cases. Some I think are pretty boring. Other are maybe interesting. I don't remember. But then you'll see it move around. I recommend that you plot. I don't think your GSIs really care whether you plot or not. They will look at the codes. But when you write this, you will make bugs. And plotting will help you catch it, or at least see if it looks correct or not. So you can plot. You take a step, you plot. You take a step, you plot. How do you do that, by the way, if you want to use my code? If you want to use my RK4, where did it go? How do you plot? It doesn't allow you, right? So you have to make a copy and put a plot at the end or something. But basically, you could do a pen plot here at the end at every step or something like that. You don't have to do it, but I think it will improve the... So, and by the way, the last step is also something you could do immediately. What do I always ask about at the end? Or at least I did in the last programming assignment. I want you to confirm that this is accurate. And you're doing one of those convergence plots again. You're running it from many H's, and you see if it seems to get better. All right? That's it. Due in 2 weeks from today. Anyway, thank you. Remember, my office hours are 11 tomorrow.